around us is an amazing place, filled with beauty and with science. And when you share the beauty and science with the next generation, magic can happen. Come and join me and my children as we share with you some experiments that you can do at home with some of the things you commonly find around the house. Welcome to Conversations in Science, Experiments with Kids.
So what are we going to do today, Mum?
Hi, I'm Judy Elmore, and welcome to a special video version of Conversations in Science, Experiments with Kids. Today I have my daughter with me, CJ, and she's going to help me show you how we can measure the speed of light. So what do we need?
We need a microwave because this experiment will not work without a microwave.
Okay, microwave.
The second ingredient that you need is a bowl and a plate so that way we can disable the turntable in the microwave.
Okay.
The third ingredient that we need is a scientific calculator and a measuring tape. You can use a ruler instead of a measuring tape if you prefer not to use a measuring tape, and a normal calculator will do just as well as the scientific calculator.
Okay, and what else do we need?
And the most important ingredient is a chocolate bar.
Chocolate. Ooh.
To disable the turntable in your microwave, remove your turntable plate and place a bowl upside down over the turntable mechanism. Place another plate in the microwave on top of the upside down bowl. Then place a chocolate bar that is about 8 centimeters by 8 centimeters into the center of your microwave and run the microwave for approximately 30 seconds. You should get a few dimples forming in your chocolate. Measure the distance between two dimples. The measurement will be approximately 6 centimeters or 2.5 inches. To find the speed of light, we take our measurements, convert them to meters, then multiply them by 2, and multiply them by the frequency of the microwave. You can find the frequency of your microwave on the back. The frequency of our microwave was 2,450 megahertz.
When people think of light, they tend to think of what we can see. But visible light is actually a small, narrow band of the entire electromagnetic spectrum, all of which is classified as light. The electromagnetic spectrum will also include things like infrared, ultraviolet, X-rays, gamma rays, microwaves, and, believe it or not, radio waves. Almost everything on our planet will emit light of some description. Even we humans, we will emit infrared light in the form of a heat source. So, to measure the speed of light, microwave is a perfect thing to use. When physicists describe light, it can be via a variety of different models, one of them being that light is a wave. In the case of the microwave, that's exactly what we're dealing with, hence the name, microwave. Waves can be described in a variety of different ways. You can have a traveling wave, which is what you would see if you were to throw a pebble into water as the motion ripples out from its origin point, traveling along the surface of the water. But you can also have what we call a standing wave, which is where your end points are fixed and everything else is moving around it. Another example of this one would be a jump rope. Go outside and see if you can actually get the rope moving in such a fashion that you can create a standing wave pattern with the middle point not moving. This middle point, if you do succeed, is what we call a node. The points that are moving around it are what we call antinodes. Within a microwave, your heating takes place at the antinodal regions, which is one of the reasons why we now have turntables within our microwaves, so the antinodes can heat the food evenly as possible. What we are doing in this experiment is we are measuring the distance between the two regions where the antinodes are actually melting the chocolate. This distance will be half of the wavelength of the wave that our microwave oven generates. We need to know the wavelength because the speed of a wave is directly proportional to the wavelength. I know this sounds counterintuitive, but the speed of which a wave travels is going to be proportional to the wavelength itself and the frequency at which it moves. It is accepted that the speed of light is approximately 3 times 10 to the 8 meters per second. If that was the case, then for a microwave that has a frequency of 2,450 megahertz, then it would produce waves that have a wavelength of approximately 12 centimeters. Half of that, the distance between 2 consecutive antinodes, that would be 6 centimeters. That's what we measured in our experiment.
So it can be lots of fun with some of the things that you have around the house and just doing basic science experiments. I know I have lots of fun with this. You have to do it a couple of times just to see if you can get it right. Why not? Meanwhile, we'll see you next time.
Oh, we forgot something!
What?
Hide the evidence!
Hi, I'm Judy Elmore and welcome to a special video version of... Why are you laughing? And welcome to a special video version of Conversations
and science experiments with kids.
Thank you. Okay. Just got giggle fits.
Conversations.
Yeah.
Conversations. Say it with me.
Conversations. Shall I have a cup of coffee or tea?
Science experiments with kids.
Okay.
You need to remember that.
I do need to remember this.
No interruptions and no mistakes, please.
Okay. Meanwhile, the chocolate is melting. Charming.
You can start now.
If you want to find out more about science or the experiments with kids, you can follow me on Twitter, that's Judy L. Moore, or you can find me on Facebook, that's Judy L. Moore, or you can visit my personal website, that's judylmoore.com. But if you have a special question that you have about science, feel free to contact me at the radio station, that's at science@KLRNRadio.com. Meanwhile, I look forward to seeing you all next time.